Shelley, and Community Ecology Lab, as well as the Denny Biomechanics Lab. He's been at Hopkins since 2009. The first 2 years he was a research technician there and is a PhD candidate in the biology program with a civil and environmental engineering minor. He has a BS in marine biology from UC Santa Cruz, where he was certified as an AAUS scientific diver and worked with PISCO as a subtitle technician along with many ML students who I gather know him quite well. He studies the hydrodynamics behind natural occurring low oxygen events in kelp forests and the mechanisms by which communities cope with these stressors. When he's not diving and studying the kelp forest, he spends his time playing music and working on his sailboat, the Wanderlust. He's here today to talk to us about the results of his research and in particular about observations, causes, and potential consequences of small-scale temperature and oxygen variability in a kelp forest system. I just want to point out that his doctoral defense is a week from Monday, so he really wants us to give him a good stiff workout today. So the tougher the questions, the more incisive the questions, the deeper the questions, the happier he's going to be, okay? So on that note, let's give Paul a big welcome.
Thank you for having me. It's fun to be here. Yeah, thanks for the introduction, Michael. So I'm a PhD candidate at Hopkins Marine Station, and I've been working on just really teasing apart some of the high-resolution physical dynamics of how particularly hypoxia works in the kelp forest and look at what it might mean for organisms. Happy Groundhog Day, by the way. So as I'm sure most of you know, in the global ocean, there exist these naturally occurring oxygen minimum zones where just below the photic zone, where we have photosynthesis and respiration, and we have respiration only, and there's not enough light for photosynthesis, we have this oxygen depletion. And that's been the case as long as we've had oceans and things living in it. But it's of more modern concern for scientists because the oxygen minimum zones are expanding with climate change. So Lothar Strama in 2008 was able to show that over about a 40-year period, the oxygen minimum zone, which is this blue area right here, has expanded in the water column, and it's also gotten more hypoxic in the interior. So just to touch base about why oxygen is important. Well, breathing, we sort of knew that. But more interesting are things like stress physiology and the modulation of activity patterns that the stress physiology can cause. The impacts of those effects on things like species distributions and movement patterns. And then together, those things can influence a lot of indirect dynamics through foraging, predator-prey interactions, some density-dependent effects with mortalities, et cetera. So Ashley Booth, who was a Moss Landing student a few years back, did some fantastic work on hypoxia in Monterey that really set up a lot of what I do in my PhD. So she looked at 10 years of oxygen data from the Monterey Bay Aquarium seawater intakes and was able to show that during upwelling season, so definitely starting around March and depending on the year ending September or October, there's just these massive fluctuations in oxygen right near the shore. And in a spectral analysis, she was able to show that the dominant frequencies in those fluctuations were the K1 and M2 tidal cycles, so the once a day and twice a day tidal fluctuations. So that was able to show that this is something to do with some kind of tidal advection. And what it was directly was internal waves. So internal waves, if you're not familiar, are large waves in the oceanic thermocline. So when we just have warmer, less dense surface layer and then a colder bottom layer, we can have waves in the boundary between the two that follow the exact same physics as surface waves, but because cold water and warm water are closer to the same density than, say, air and water, the same perturbation energy that would create a surface wave that's about 1 meter tall can create an internal wave that can be 100 meters tall. because of that, these can be very important transport mechanisms for deep water into shallow waters. More specifically, what we look at in coastal areas is internal bores. So a bore is just a term for a wave after it's broken, and a wave has to break in order to actually transport mass from one place to another horizontally. And so just like surface waves, when internal waves approach a sloping bottom, a sloping bathymetry, they will shoal and break, forming bores, and then roll into the shallow systems. And so when these internal waves are coming from dense oxygen minimum layers, they can create pulses of low oxygen water in the shallows. So Ashley was able to show that on an average event in the Monterey area, say take an average 24-hour cycle when oxygen is fluctuating, you might see some kind of tidal-looking fluctuation in oxygen, but it also covaries very strongly with temperature, with pH, with salinity, also with nutrients and anything else that would be directly tied to these deep water masses. And so whenever we have a low oxygen event, it's going to be cold, and it's also going to be low pH and any of these other things. And then so we might spend some time below. This line is commonly the 4.6 milligram per liter oxygen line, which was defined to be a very important threshold for impacts to ecosystems across the globe. And during these low periods, it may spend some time below there. So the central questions of my overall dissertation are, what are the relevant scales of the spatial variability inside the kelp forest that these internal bores cause? And then in a little bit more detail there, parsing one of those particularly interesting mechanisms that internal bores drive, which is something that I've been calling the internal tide pool, and I will get into that in a little bit. And then finally, what are the potential consequences for kelp forest organisms? Because of some time considerations today, I'm just going to focus on the first two because they're much more directly tied together. But in questions or afterwards, I'm happy to talk about number three as well. So the way we can see internal bores is using thermistor chains. So a thermistor chain is just, we take a big heavy weight and a really buoyant buoy, and we use a line that is short enough that it keeps the buoy underwater all the time so that the mooring line stays taut. And then we can suspend these individual temperature sensors up through the water column. And so we can get a time series of water column temperature and create a temperature contour plot, which gives us a picture of the bores in actually some major detail. So if we look at one of these temperature contour plots, this is water column height on the y-axis and a function of time. And I'm going to take some time orienting you to this plot because we're going to see lots and lots of these things throughout the talk. We see that, so these, I don't know if you can see my tick marks, but these are on roughly an hour scale. So this is a 8-hour or thereabouts bore. And we see that we see this very large cold water mass where the thermocline here throughout time raises and stratifies the water column and then drops back down, and that's a single bore. And so if we're looking at what we call the bore arrival, which is sort of what you see in this cartoon here, when the bore is initially contacting the thermistor chain, we'll see a rising of the thermocline, and then during what we call the bore period, the bore has inundated the entirety of the water column, raise the thermocline up as high as it's going to raise for that particular event. And the bore is neither arriving or relaxing. That's kind of the moment where it stays still and turns around just like a wave on the beach. And then during the bore relaxation, the thermocline can drop very rapidly. We often see advection of surface water back into the shallows over the internal bore because that's what's been displaced by the bore, and now it's rushing back in. And that can sometimes cause some downward advection of surface water because of just the downward mixing of the shear in this situation and just the concentration of that water rushing back in. And if we look at temperature and oxygen over the course of a summer, so temperature here is in green, oxygen is in blue, I will tell you that when we have periods of internal bore activity, that's when we see by far the largest fluctuations in both temperature and oxygen, and they co-vary, versus a period where we had much weaker bores and temperature and oxygen don't fluctuate as strongly. But my questions are really all about what happens when the bores get into the kelp bed, and what does that mean for spatial variability? So I want to know, well, do the internal bores create spatial variability on small scales? And if they do, what are those scales? How large is that variability? And what exactly about the bore, sort of mechanically, is actually creating variability across a small reef? And just to go back to our roadmap, this is all kind of bundled under big question 1 about what is the variability. So we know that when we see surface waves crashing on rocks in the intertidal zone, of course they break, but as they hit the rocks, I mean, they don't stay one nice clean wave. They get broken up and they reflect and diffract and bounce off of everything, mix, and just turn into a big mess. So when you look at the kelp forest, we see that there's large rocks and kelp that's of a similar scale relative to those waves. And I really saw no reason that internal bores couldn't get broken up by this topography, just like waves at the surface do by topography in the rocky intertidal. So the hypothesis here is simply that these internal bores are broken up by the kelp forest and reef topography, and that's what will create all of this variability. So my study site, this isn't the best picture, but this is Hopkins Marine Station. You guys are over there somewhere. And I'm working just in a small area of the kelp forest right off the coast of Hopkins. This is north, and that can confuse people sometimes. You guys probably are more oriented, but because we're on the inside of the Monterey Peninsula, offshore is east, even though we're on the west coast. And so the bores come in from just right out here. The working hypothesis is that they're originated around the mouth of Monterey Canyon. And so they propagate in about on this angle and relax something on that angle. And so we can look at those dynamics in this study site right there. What I've done, just a rough schematic of how my measurements are taken. I have a thermistor chain, as I described before, kind of centrally in the kelp forest. And I have a number of sites in which I've deployed either mini dots, which are a dissolved oxygen and temperature sensor, or just Seabird SB39 temperature sensors. So I have some sites where I have temperature and oxygen, and some sites where I just have temperature. And I've targeted these areas of high topography in the reef, where I had, for each site, I had a pair of sensors, where one sensor, which we'll call the trough sensor, was placed in the depression of one of these areas of the reef, right next to where there's sort of an adjacent high topography rock. And then we have the ridge sensors, which are on top of that rock. So we can look between these two. The ridge sensors hypothetically reflect more of what the water column as a whole is doing versus compared to what we see down within the topography. And so just looking down on my site map, this is a very, very rough look at the layout of the reef in the area that I'm working at Hopkins. The cyan dots are the dissolved oxygen and temperature sites, and the yellow dots are just temperature. And my main thermistor chain is right here. And so when bores are coming in this way, the thermistor chain is relatively central to the site, at least in the cross-shore direction. And then, yeah, the spatial scale of this is about 50 meters longitudinally and about 90 meters latitudinally. And some of the measurements we're going to be looking at are, we care about both the variability among sensors and also just absolute differences at any point in time. So one of those differences is the vertical difference within the topography, which is just for any instance, for any time point, would be just the trough temperature subtracted from the ridge temperature. So some large number there would mean a large difference between these two. Or we could also look at between sites, pairwise differences between sites. So we would take, in this case, the absolute value, so we don't have to look at everything both directions, just the difference between one site's ridge or trough sensor and the other site's ridge or trough sensor. And then lastly, when we're just talking about variability, we might take some group of sites, and for every time point, take the standard deviation amongst that group, and we can construct a time series of variability across some expanse of the reef. And so to just orient you to some of the things we see, the play button's really small on the screen, but we're going to looking at this plot. In this case, we have the site map of all the ridge sensors on the left and then the trough sensors on the right. And here's our thermistor chain where the color maps between these match. And so the color of the dot in each of these is the temperature at that particular site for the instance in time represented by the vertical dashed line, where this is the thermistor chain. Reminds you that that's right there. So this is we're going to look at the arrival of one internal bore and just what happens spatially amongst all these sites as far as sort of the mosaic of temperature that happens as this thing arrives. And so the internal bore starts to roll into the kelp forest, and we see patchiness amongst the trough sensors first, but not in any particular order. It's not like it's cleanly moving in from one part of the reef to the other. We see a lot more variability at the trough sensors before we see the ridge sensors, but then as the internal bore starts to fill the water column, the variability starts to go away in the trough sensors, and then later on, the variability also starts to go away in the ridge sensors. And so this looks like the water column, the thermocline raising through the water column as it inundates the whole water column. As the thermocline starts to pass the various sensors, it's driving variability, but as it's filled the whole water column, you can basically presume that all of these sensors are within the internal bore. So you can take my word for it that between the arrival and the relaxation during the bore period here, there wasn't a whole lot of change in the variability, but things are also interesting in some new ways on the bore relaxation. So as the thermocline begins to drop, we see some really high frequency temporal variability in the spatial variability at the ridge sensors that's not so much echoed at the trough sensors. That's presumably due to a lot of this sort of high frequency fluctuations that occur on the relaxation front of the internal bore that presumably don't translate down all the way to the bottom of the water column. But as the thermocline has dropped past the height of our trough sensors, we're left with an interesting condition, below the height of the ridge sensors, we're left with this interesting condition in the trough sensors where we have this large variability amongst the topography. And going into the internal tide pool things in the second section, I'll be referring back to that. So stay tuned. But as the internal bore continues, I'll get this right eventually. As the internal bore continues to relax, we see the patchy variability of the trough sensors gradually decrease, presumably because eventually this internal bore water finishes draining out of all the topography, and we're left with the well-mixed state again that was there before the bore came in. So one of the ways we might want to look at topography, or look at spatial variability, is to just group some sites by proximity to account for variability that would just happen because of large-scale differences in when the bore arrived at a site. And so we'll take this group of inner reef sensors and look at the standard deviation across them for every time point. And what we see is that during these summer periods where we had a lot of internal bore activity, we see some pretty large spikes in this variability. So across that small patch of reef, standard deviation in temperature of up to 2 degrees centigrade is a pretty high variability. Versus when we have these no bores or even just weaker bores that are less stratified or smaller, we see lower variability, about half that magnitude. And if we really zoom in on what's happening for particular bores with that variability across an individual bore event, we might convince ourselves that variability in a group really is, you'd call it like framing the internal bore, where the spikes in variability occur during the arrival front and the relaxation front of an individual bore, versus the corresponding variability during the bore period and also these interbore periods, just periods between the bores, is pretty low. There's a kind of a detail exception to that, which is just when the internal bores themselves are not terribly large and don't really fill the whole water column. The thermocline in this case is probably sloshing around at the height of all our sensors, and in this case we see a spike in variability that sort of lasts throughout this train of small bores. But that's just a side note. If we look at the vertical temperature differences across all of our sites, so this is just a time series of all of those vertical differences, the trough sensors minus the ridge sensors temperature. During these periods where we had lots of internal bore activity, we see some huge spikes in temperature difference at that small spatial scale. And I think I forgot to tell you earlier that the rocks in this area of the reef are 1 to 2.5 meters tall. So the spatial scale creating these large vertical differences in temperature is within 1 to 2.5 meters. So when we have these internal bore activities, we see temperature differences on the spatial scale, up to above 5 degrees centigrade for brief moments in time, and commonly above 2. And all of these are pretty big differences for ectothermic organisms that live in the kelp forest. And then if we look horizontally at what the horizontal temperature differences are during this process, we see not quite the same level of differences, but still very high. And what I'll tell you is that with 13 sites, there's a lot of pairwise comparisons that I could make. Shown here is only sites that are within 10 meters of each other. So the spikes in variability, the spikes in temperature differences that we see between sites are spikes that are occurring on a 10-meter scale within the kelp forest. And once again, they are commonly above 1 degree centigrade, often above 2, and sometimes above 3. So still big temperature differences to occur on that scale of a reef, which happen during internal bore activities. Now, we sort of set this up that this was primarily important because we care about oxygen. So I've taken all of my sites that I had an oxygen measurement and just taken the standard deviation in temperature amongst those sites as well as the standard deviation in oxygen amongst those sites. Just because of unit differences between temperature and oxygen, you have to scale that standard deviation to the total range. But when you do that, you see that the magnitude of the variability relative to the range of those fluctuations is about the same size for oxygen as it is for temperature. So because oxygen and temperature co-vary so strongly because of the advective processes that are driving this and the correlation with the water masses, any of this variability that we see in temperature, we can just as easily expect to see it in oxygen or pH if that's what you're interested in, or nutrients or anything else. So to kind of conclude this section, we've seen that there are very large spatial variabilities at small spatial scales during periods of internal bore activity, and that the vertical and horizontal spatial differences follow sort of the same story as what we see if we just look at variability as a whole. But the timing and the dynamics of these variabilities are pretty consistent with what you'd expect by this hypothesis that internal bores are being broken up by the topography. To really nail down exactly how the internal bores are being broken up by the topography, we would need a very, very good, detailed measurement of the topography itself and very, very high resolution hydrodynamic measurements across that topography, which is a hard thing to do, especially in the kelp forest where we measure hydrodynamics with acoustics and the water column's full of kelp. But the patterns and variability that we see and when we see them are pretty consistent with that hypothesis. So moving on to sort of question 2. I mentioned earlier that during this relaxation, especially within the topography, there's this period when the bore is potentially draining out of the reef itself more slowly than it would absent the reef. And I've broken that down into what I've described as the internal tide pool. And so we're going to look at what that looks like. So if we look at the topography in the kelp forest, I'm sure many of you have dove in kelp forest before. I mean, the topography is not homogeneous. There's often these very profound or pronounced depressions in the topography that are commonly gathering points for sinking material in general. And this is just like depressions in the rocky intertidal, which can trap surface waves and surface tides. So if there's something that we call an internal tide pool, we might expect that during the arrival of the internal bore in the kelp forest, the bore is sort of penetrating a well-mixed water column that's high oxygen, high temperature everywhere, and the bore itself is cold and low oxygen. During this bore period, the internal bore may occupy the entirety of the water column, and the water column will be very stratified with the oxygenated warmer water restricted to just the top surface layer. And if we were to look spatially across the reef, we would see low oxygen and cold water just about everywhere like we saw in the last section. But an interesting thing can happen during the relaxation, where we can just see here that the internal bore in the water column above the topography is unimpeded by anything other than kelp. So the kelp presumably imparts some drag on the water column. But really, now within the topography, you have you no longer have a direct path offshore. The water has no choice but to find its way around the rocks. And if the rocks are relatively enclosed, that could be relatively retentive. And so after the internal bore is relaxed, you may, at least for some period of time, have this condition where you have cold, low oxygen water trapped within the topographic depressions within the reef. And that will persist until something breaks it up. Eventually the reef, if these depressions are bowls, none of them are bowls that don't have cracks in them. So the water will make its way out through that way. Also, you could have vertical mixing that will mix these out, but at least for some amount of time, we could be left with this condition. And so the simple question in this section is just, is this really happening? Do internal bores actually create what you call an internal tide pool? So this would be a pretty boring talk if they didn't. So I'll show you. I'll show you what I found or how I went about measuring and looking for them. So you've seen this kind of configuration before. This was actually a few summers ago. in summer 2014, I didn't have all of the sensors that I had for the past experiment, but I had 2 pairs of these mini dot dissolved oxygen temperature sensors that I targeted 2 sites in the kelp forest, and once again had a trough sensor and a ridge sensor where the trough was in the trough. In this case, I took great care to put, because I only had to find 2 sites, I took great care to find 2 sites where the trough sensors and the ridge sensors could be at exactly the same distance from the free surface. So any of these dynamics that are driven by just background stratification and a depth difference between the sensors, we're not looking at here. And in this case, I had a thermistor chain, but the thermistor chain was offshore, and it had thermistors that were also at that same height from the free surface. So we can use this configuration to compare what's happening in the water column at 2 sites in the kelp forest at the same height as compared to what's happening at that same height in the water column where you don't have kelp or topography, and the same is true for the trough sensors. So the trough, we call these the trough equivalent and the ridge equivalent thermistors on our thermistor chain give us a comparison to the reef, give us a sort of topography and kelp absent comparison to what you'd expect to see in the internal bore relaxation as compared to what happens when you have the effect of kelp and topography. If we look very closely at a single internal bore event in the kelp forest from the perspective of just one of these sites right now, we see that during the internal bore arrival, temperature and oxygen at this site, so temperature is in green here, oxygen is in blue. The time scale is on the hour scale. And the trough sensors are solid lines, while the ridge sensors are these dashed lines. We see that as the bore sort of starts to fill the water column, we'll see a drop in temperature and oxygen, some stratification still, so some vertical differences in temperature and oxygen between our trough and ridge sensors as the internal bore hasn't fully filled the water column. But then during this bore period, when the bores come into maximal residence in the water column, the thermocline is as high as it's going to go, we see that both temperature and oxygen between the trough sensors and the ridge sensors are reading almost identically. So during this period, there is almost no vertical difference across the height of the reef topography. But then during this relaxation period, it gets interesting. Where, as we showed before, where the surface water can maybe come rushing back in over the bore, and we actually see some downward advection of really warm water, we'll see that at the trough sensors, both temperature and oxygen, their readings will jump up very drastically on the order of minutes. So just as the thermocline starts to drop in the water column, those readings will jump up very high very quickly. And then over the course of several hours, the temperature and oxygen readings will recover much more gradually, and it's not until several hours later, and even after the bore has been absent for at least an hour or two from the offshore water column, that's when we see both the temperature, the trough and ridge sensors reading the same again, back to sort of reading the well-mixed water column state. And so if we want to quantify this, we might care about that vertical temperature difference between the ridge and the trough site. And we also might care about the slope of this relaxation curve. So this is a measure of just how quickly is the relaxation happening, as indexed by the derivative of temperature and time. So just how quickly is temperature changing. And it's really the difference is because between these 2 sites, we see that the ridge sensors have a very similar dynamic where they jump up to their higher readings. It's really the differences at the trough sensors and how they recover that drives differences in the temperature and oxygen from site to site. And so it's these trough relaxations that we're going to be comparing. Now, this is more than just a mess of squiggles. If we're going to compare across a number of sites and sort of construct what we think, what you call a canonical recovery looks like, that is sort of the characteristic recovery or relaxation dynamics for a given site, we have to contend with the fact that not all bores are the same temperature, and not all surface waters are the same temperature, and we have to somehow account for those differences in order to compare across a number of bores and construct that sort of canonical recovery. But we can do that. The way that we selected our relaxation times ended up allowing us to hold the time axis here constant across all of the bores. So all of these windows are about 6 hours. And so we can normalize temperature by their total range. So now temperature is dimensionless, varying on a scale of 0 to 1, which is just the temperature at any point in time is expressed as a proportion of the range in temperature across that time. And now we're all on the same scale, and we can average across all of these. We can average across each of these relaxations for every time point and get a mean relaxation with an error estimate around that. And so that's what we call this canonical recovery, where we have a mean relaxation and some sort of shaded error region around that. And so if we look at the different sites in the kelp forest as compared to offshore, so in this case, the two sites in the kelp forest are the purple and the cyan colors, while the offshore thermistor chain is green. And again, the ridges are dashed lines and the troughs are solid lines. We see that, well, first off, inside the kelp forest and in the unobstructed water column at the offshore thermistor chain, we see that all of those relaxations really group together. None of them are significantly different from each other at any time point across this relaxation. And what's interesting about that is the trough equivalent sensor, this solid green line at the thermistor chain, also groups with those. But the sensors that are different are just the trough sensors within the kelp forest. So the trough sensors in the kelp forest lag the relaxation at the ridge sensors in the kelp forest, as well as their depth equivalent sensor in the offshore water column. And so it's the difference between these two that might tell us that there's some sort of impedance of internal bore relaxation by the topography. There's supposed to be a figure here that I don't know where it happened, so we'll skip that. This would have told you that if we look at that relaxation rate, it was also slower in the kelp forest, and so basically all of the different ridge sensors, as well as the ridge equivalent sensor, have one higher relaxation rate, especially during the initial period of the relaxation, while during that same period, the kelp forest sensors are relaxing much more slowly, is what you would see here if there was science there. Never fear, we have more data. So if we just look at what is those vertical temperature differences across this height of the topography, across this relaxation. So now, once again, we've subtracted the ridge temperature and the trough sensor and the trough temperature, in this case, sort of the dimensionless temperatures. But we see that across this recovery time, the kelp forest topography maintains almost twice the vertical temperature gradient that the unobstructed water column retains. So during this recovery period, there is a much higher temperature difference across the height of the topography than you'd expect just by the unobstructed water column. And really, that difference can persist to some extent for a long time. So here, sorry, I didn't really orient. Time 0 is really the beginning of the relaxation, and we included some time before that so you can capture the transition into the relaxation. I should have told you that earlier. But even 2 hours out from the onset of the relaxation, we still see some difference in the the vertical temperature gradient within the kelp forest from what we see offshore. And once again, just to show what we might expect from oxygen. So I didn't have, in the offshore thermistor chain, I didn't have an oxygen measurement there, so I can't show you a comparison in oxygen within the kelp forest directly to what we see offshore. But if we just look at all of the events that actually had low oxygen against, and look at the vertical temperature difference at one of the sites against the vertical oxygen difference in one of those sites, we see that the vertical temperature differences in temperature and oxygen are very similar. So, and this is a very similar dynamic to these plots. So I think it's safe to presume that when the kelp forest is holding on to a large vertical temperature difference, you can expect that to reflect the difference in oxygen between the oxygenated surface water and the internal bore that filled our pool. So to conclude this sort of section, I think I've taken this as pretty good evidence that these internal bores really do, or these internal tide pools really do happen in the kelp forest. And I think I can say that because we have this retention signal of this denser internal bore water within the kelp forest and reef, but that retention signal is really concentrated below the height of the topography. So if this were some effect of, say, drag of the kelp forest as a whole, we wouldn't have expected the ridge sensors and the ridge equivalent sensors to really group so tightly together across all the sites. We would see some lag between the ridge equivalent sensor in the offshore water column and the ridge sensors in the kelp forest, but we don't see that. We really see that all the differences are happening within the kelp forest trough sensors. So that looks like some impedance of the rocky topography itself. And we've also shown that when oxygen and temperature co-vary, these things could potentially prolong hypoxic events for critters that live in those those depressions in the rock, which many of them do. So to sort of step back to what some of our bigger picture points were here, I want to point out, as far as the real importance for ecology, is that these are large spatial variabilities, and they're really reef scale. And by reef scale, I mean these variabilities exist for various amounts of time at the spatial scale of the habitat use of your average kelp forest mobile organism. So when we're having these variabilities between sites that are meters apart, it would be intuitive that matters for kelp forest fish that are distributed across and move across the habitat at that scale. And the ranges of these variabilities, so the differences in temperatures, the differences in oxygen, are well within ranges that we can say, or that are shown to affect organisms in various ways. They're not small differences. So it's intuitive that we might see some shifts in distribution of some of these species at these scales around some of these events, or other behavioral effects or other physiological effects. And then I think the other reason that this could be important is I think it could inform just how we do certain kinds of subtidal ecology in some interesting ways. I'll take a step back and say that in the intertidal zone, there's been a lot more arguments made about how things like solar irradiance and differential splashing of sites and lots of other effects, wind exposure and things, can create really fine-scale mosaics of very large variability across just within one intertidal site. I think here we can say that there's a similar kind of variability happening on a little bit of a different time scale, but across a similar kind of topography within a kelp forest. And a lot of the times when we do some kinds of ecological work in a kelp forest, we'll characterize the oceanographic environment from that site with one sensor or one mooring. And while, of course, like lots of times that's the only thing we can do, that may not always, depending on your question, that may not always reflect what the kelp forest as a whole is doing oceanographically. So there are probably plenty of questions where this sort of fine-scale variability isn't a big factor. But for some kinds of questions that are very spatially and temporally explicit in their measurements or in their analyses, so not that you're necessarily trying to tie the ecology to that spatial scale, but the measurement that you take represents a very specific place and a very specific time, and you're treating those measurements as different measurements. These variabilities may be important in some of your data. So some of the examples of that I can think of off the top of my head are things like tagging and movement studies, tethering and predation rate measurements, where you might have tethered things and looking at the predation rate on tethered organisms that are put out at all of the same, or they're distributed across space in the kelp forest, but that predation happens on a relatively fine time scale, and presuming that the fish and inverts that are interacting there are all ectothermic. If there's variability amongst those sites that you're not measuring for, that could influence your results. Also things like moored camera work and fish follows. But I think also just, if we think about when those things are occurring and just try to pair some of those measurements with a really specific measurement of even something like temperature, you can say an awful lot about what else is happening. And so with that, I think I'd like to acknowledge, all of the people that have funded me. None of this would work. Couldn't do any of this kind of work without lots and lots of very competent field help. And I'm eternally grateful for the people that have helped me there, and a great committee of advisors and people that have provided me sensors and things. And I'll say thanks. Yes, sir.
Hopkins is a notoriously calm kelp forest. And so I'm wondering how much
True.
of this would seem very logical in very calm water. How much of this would hold in a more exposed area like off 17 Mile Drive, where you've got a lot of surface swell coming in and a lot of water movement on the bottom caused by that?
Oh, sure. Yeah. I mean, there are reasons to think that some of this could be washed out. So just when you have a lot more wave action at the surface and a lot more vertical fluctuations in the water column, that could create mixing that translates down there. I'll also point out that in that area, the topography is higher too. So the answer is we really don't know. And if there's vertical mixing, I mean, it could wash some of that out, but there could still be some of these differences at a different time scale. So yeah, I mean, I think it could go either of those directions, and we don't know for sure.
Do you think like this last week, there were enormous waves off Lower Point, I'm assuming at Hopkins too, right? You had your sensor gadgetry out there, and a boar came in at the same time, and you see it?
It's hard to say. Probably, I mean, those were some big waves, and so yeah. Yeah, I don't really know. I mean, so presumably that would have a pretty large effect, because the larger waves their wave action would translate a lot deeper and really create a lot of mixing. But that's not, those waves of that size aren't super common at Hopkins. Yeah.
So one of the conclusions was that in this system, the kelp itself was having very minimal impact, based on what your suspicion was. So is that because the kelp itself, or at least whatever kelp was present at your site at that time, individually does not have enough drag to impact the flow, or is it because the topography relative to that drag imposed by the kelp is too high? So had you done this at Point Loma, which is extremely flat with extremely large macrocystis plants, relatively widely separated, would you therefore expect to see a higher impact of the biological structure than the topography itself?
Potentially. So it could go either way. I mean, I think, yeah, if you had a much denser kelp bed, you could see a larger scale retention effect on the water column as a whole. I guess we saw in the first section, we saw a lot of variability among sites at the ridge sensors as well. And presumably, if you have patchy drag, which you often do if you have like a mature kelp forest where the kelp forest is composed of a smaller number of really dense plants versus a larger number of diffuse-type plants, that drag is going to be patchy. And not that it'll necessarily break up an internal wave, but it could differentially it could put differential drag effects on it across the water column and really kind of change the sort of the shape of the wave front, which will influence topography or influence spatial variability as well. But I think, yeah, in either case, a different kelp forest would create more retention, maybe less variability, but it's hard to say. There's been a lot of work on the hydrodynamics of kelp on higher frequency fluctuations, so getting into things like wave frequencies, and that the kelp has a pretty large damping effect on those frequencies. So the kelp will damp a wave until it's stretched to its limit, and that effect can get rid of some of the vertical mixing that can happen. And so in that case, the kelp, if vertical mixing needs to be dampened in order to allow retention within the topography to stay patchy, I mean, the kelp could facilitate patchiness as well.
I was more interested in the fact that if you could imagine a scenario in which the kelp itself would benefit or would enhance retention, right? The fact you were arguing, well, you weren't arguing, but you were bringing up dissolved oxygen for
Sure.
kelp forest organisms. Well, in fact, dissolved oxygen is going to be inversely correlated with essentially CO2 or nutrients that are beneficial to the kelp. So if it's enhancing retention because of its own patchiness,
Right.
that water is itself going to be beneficial to the kelp that's enhancing the retention. I was looking for a positive feedback.
Oh, sure.
Whereby
Yeah.
a denser kelp forest, if it's able to retain more water from the bore, is it able to retain more cold, nutrient-rich, higher CO2 water than had it be a less dense kelp forest? And I can imagine some positive feedbacks in that case.
Oh, sure. Yeah, that's presumably true. How much so, I'm not sure.
Okay.
And yeah, because that's going to, the amount that would extend that residence time and how quickly the kelp can uptake those things, I don't know. But yeah, that's reasonable. Yeah, Michael.
Given that you made the analogy with the intertidal zone and the actual tide pools, which are going to have a kind of a very different ecology to them, are you finding, or would you hypothesize that within those kelp forests, within your inner tide pools, they too will manifest in a particular community, a particular ecology that you wouldn't see without that eternal tide pool effect?
Potentially, so the extensions of, so there's I was focusing on the arrivals and the relaxation because that's where this sort of novel process happens. But in between those two things, there's what we think of as the hypoxic event, which is the large-scale internal bore. And so that is 10 to 20 hours long. That's a rough guess. And then the extensions we're seeing on that based on this retention are a few hours. And so for something, for lower metabolism organisms like urchins or even just like benthic organisms that are attached to the substrate, I sort of have my doubts that extension by the topography is large enough to really make a difference for things that are their metabolism so low that extension isn't really a big one. But for things like for mobile organisms and things that are higher metabolism, that have the ability to shift and move around these pools, but use those pools as habitat. I think that actually some of my colleagues had some tags out this summer and we're waiting on the data back. I think it's reasonable to think that in the mobile organism community they might be moving around this variability. And then the ecological implications of that have to do with how does predation efficiency change if, say, the rockfish suddenly avoid their main habitat and concentrate themselves in some areas where it's not hypoxic, and what happens if there's a big lingcod sitting there or something like that. So I really think it's the mobile community that will see more of those kind of effects. But we need to measure. Yeah.
Earlier in your talk, you said there was the critical threshold was around 4 milligrams per liter dissolved oxygen for almost somewhere around there. I was wondering, during your time where you had your sensors out, did you encounter any of those events where they dropped that low? And if so, how long did they last, or anything like that?
No, you got to do that to me, don't you? So I happened to do this research during 2 El Nino years. So there wasn't. So we saw some events. I had 1 week where we saw some low oxygen events, and in those cases it would be below 4.6 for the length of the internal bore event. But in the particular years that I was doing this, there wasn't a whole lot of upwelling, and so I mean, I didn't really get into upwelling in the effects here, but upwelling has to draw the oxygen minimum zone up shallower in order for the bores to really become hypoxic. The kinds of bores that I have during upwelling years, they are very frequently hypoxic, and when you have strong upwelling, most of them will be near 4.6. 4.6 is a threshold taken from, was a global like meta-analysis across all organisms that have been shown to be affected by hypoxia. Really, very few or none of them actually came from this system. So whether or not 4.6 is actually a really relevant threshold to these organisms, we're not sure. I mean, I think there's a lot of people studying hypoxic effects on organisms here to really see what's the actual important oxygen level here. But yeah, during a standard upwelling season, in a week where you have lots of internal bores, it will spend, most of those bores will be down.
What year did you have your sensors out?
So these were summers of 2014 and 2015. Yeah.
So,
Patrick.
sort of piggybacking on that, how do you think the difference in temperature between a bore and, say, 18 degrees C, like really anomalously warm water, how do you think that affects sort of the stability of the retention of these pools?
Oh, so like how much is?
Well, it's really stratified, right? Between the bored water and sort of the blob water or the El Nino water. So how is that representative, or how do you think that system would work in sort of a normal year,
where it's more stratified? Or?
Well, it's less stratified. The difference between the bore temperature and sort of ambient temperature would only be a couple degrees instead of 8 degrees or whatever you were.
Sure. You might. It would be nice to get some real measurements on this sort of thing, but I could imagine. So the propagation speed of an internal bore is driven by a density gradient, and so presumably in higher stratification, there's actually more gravity draining these pools, or because it's if you think of, if the bore gets broken up, it's one big bore getting broken up into much smaller bores, but each of those are still going to be driven. Their propagation speed is going to be driven by a density gradient. So I would think that if you have pooling when it's less stratified, I mean, I'm mostly speculating right now, but you could presume that if there's less of a density gradient, you actually might retain longer or drain more slowly. Did I convince you?
Okay, do we have any more questions? If not, then we're thankful for
Thank you.